so that you can have a background in what we are doing. Okay. And then I also want to mention that after the training today, if you want to receive a certificate of training, um, it's you can just for a little token. Unfortunately, we spent so much in because I had up to 1,000 participants. So I was thinking that everybody will attend. So I bought Zoom link and the licenses up to 2 times. So we spent quite a lot of money, and even the course materials, even your certificate too. So if you need a certificate, if you're in Nigeria, it's just 5,000. And if you are an international participant, just $5. I don't know whether it's okay. I wanted to make it free initially, but I think it's fair to have just a little fee for certification. Just a certificate of participation to show that you attended this training and you have you were here. But beyond the certificate, please, my goal is that you have the skill. That's why I sent out the slides to everyone to be sure that you can go over the slides at your leisure time. And every of the steps that we want to take now, you can always repeat it when you are alone. Okay? So thank you once more for joining. Thank you for coming. Let's start leading this. Yeah, $5. Yeah, it's fair. It's fair. Just a token. All right. So I believe all of us, do we all have STATA? Do we all have the software? Do we all have the software? How many of us have
I
STATA?
do have.
Okay. Okay. I am using version 17. So I know that the latest version is version 18 now. I've not upgraded mine. We need to do that. Okay. So yesterday we started with introduction. Yeah, someone is raising his hand. Please,
Yes,
someone
thank you
raises
so
hand.
much.
Yeah, Moses, go
Yes,
ahead.
I'm asking how are we going to pay the $5 for international
Okay,
students?
I'm going to send it to your mail. I'm going to send it to your mail. You're going to
Okay,
use the link. Yeah,
okay.
yeah.
Thank you so much.
So once you do that, I will see it, and by next week you have your certificate of participation. It's going to be it's a signed certificate, so you can use it for your anything you want to use it for. Okay.
Sure, thanks.
So welcome again. Let's run through the theories a bit before we get straight to the practicals. I hope I'm recording. Okay, yes, I am. All right. So yesterday we started with what survival analysis is, why we analyze data using survival analysis, how do we set our data for analysis, how do we create life tables, how do we plot this. We are going to do that practically now. So in addition to this, I also, the do file I shared with you, I did that purposely so that you can always refer back to it. Each time you have your survival data, you can just remove the variables in the do file and run the commands, and then you have your results. So I made it so that it will be easy for everybody. Okay. So we said the reason why we use survival analysis is because we cannot account for time and sensory use when we do the ordinary t-test or the other analysis that we do. So it ignores the time element and the issue of censoring does not come in. Okay. So we did a lot of quite introduction. So I want us to go straight to um, the yesterday I introduced this. I showed us how several participants can be co-opted in a study, and then at several times they will develop the event at different times. And you see this participant entered this time and develop the outcome of interest, which is death, at 5 weeks. So the survival time was 5 weeks. So this patient passed through the study and didn't develop the event. Maybe he developed it later, but so he was censored out. This patient too entered the study later and did not develop the event. He withdrew from the study. This guy entered the study, went later at this point, and then went through the beyond the study time. He didn't develop the event. So this one was lost to follow up. This one developed at a particular time. So when we gather the data of all these people, you know that in survival analysis, the two variables that are important is your time variable and your event variable. So you must always, yes, the censored patients will be included in analysis, yeah. So the time variable and someone is asking he doesn't have a dollar account. Yes, there is a dollar account that we pasted in that link. Don't worry, you see it. Once you do you can upload this somewhere. So that will not be a problem. So all these variables will be collected. So it's of course, when you are doing a cohort study, whether a prospective cohort or a retrospective cohort or a clinical trial, that's when you have time. You know, longitudinal studies take time. So you follow up a group of people. You may begin with, maybe you want to follow up 100 patients, but you may begin with 50. And then another time, another 10 join, another 5 joins, another 20. Just so you record the time that each patient joins, and then the time the person is expected to develop the outcome. So that is, at the end of the day, you have this type of data where you have for each participant the survival time and people that develop the outcome. The outcome here is a failure, which is 1. So anybody that did not develop the outcome, whether the person dropped out, whether the person withdrew, whether the person did not develop it at the end of the time period, you note it down as 0. So that is the censoring that we talked about yesterday. Okay, so let's go straight to our state that I told you yesterday that there is a non-parametric model, there is a parametric model and the semi-parametric model. So when you open up your STATA software, this is what you're expected to see. So this is my software. This is my software. This is my license and my name. So when you buy your software, for those of people asking me yesterday how they can get the STATA software, well, I think there is a place people get the cracked version, but I don't advocate that. It's not. I think it's not legal. So you can write to STATA, go to their website, apply for it, pay your money, and they will give you your own license, please. Okay. So yesterday I said that when you come to your software, the first thing you do is to call up your data. So the data we are going to use for this analysis is one popular data that the cancer research data that is very popular. So it's embedded in STATA naturally. You know, there are data that comes in STATA just for learning and demonstration purposes. So of course, we know what a do file is. A do file is where you store your commands and where you run your commands so that it can be reproducible at any point, and you can share it with your colleagues and collaborate with others. So if you want to pull this data from STATA, you use this command here. Once you say web use cancer, this data will be pulled out. You see, the data is now here. When you say browse, you see the data here. Please mute your mic, mute your mic, mute your mic. Thank you. Okay, so you see the data here. This is the study time. This is the event data. This is other covariates, drug, age, and then these are something like this is the study. This is the outcome here that has been recorded as 1 and 0. That is people that died and people that are alive. And then this is the time data. But now, because I don't know everybody that is on this call, so I want to use the normal importing from Excel. So I will close this up and I will open it back. And I will, because I share the data to you from Excel, I will use the Excel method of importing. So I'll come to File, I'll come to Import, I'll come to Excel Spreadsheets, and I'll go to Browse. So this is the data set here, data web cancer. So I'll click on open. So remember that when you want to open your data in STATA, you usually will select the sheet where your data is stored, and then you usually will tick this import first row as variable name. Okay, so you have imported your data. Once you import your data, you look at your variables here, they are all populated. So you can use either the browse window or the edit. You can go through the edit window if you want to make any change to your data. You can use the browse BR and go through. Now you see that some of them that are categorical variables are red in color. So this is your event variable, it is red. This is your covariate, it is red. This is another covariate, it is red. It is because they are all string variables. And unfortunately, STATA will not use these variables like this the way they are if you don't transform them or if you don't include them. So quickly, we'll run your encoding. You will say you can use the command encode. What does encoding mean? Encoding means to assign values to your categorical data. As you have sex here, as you have died, as you have drugs and age. Now, let's define this. Let me show you something. These two variables are the most important in this analysis. Please note, whenever you want to do a survival analysis, I told you there are two most important variables to look out for: the time variable and the outcome variable. These other ones are covariates. These other ones are just independent variables that you want to see what is the effect, what is the distribution of a survival estimate in people that had this drug versus other drug, in people that were males versus females. So these are just independent predictors or independent variables. Okay. So your outcome variable will always be the outcome here, which is people that died, will always be 1, while the people that did not die will be 0. So that is how we are going to encode this right now. So the first line of code, you say encode died, comma, generates a new variable. So you can call it death. And you enter. Now, STATA will generate a new variable for you called death. Now, if you tabulate this variable and you say no level, for example, no level, you will see that STATA has given it 1 and 2, the level of 1 and 2. This is not what you want. Okay? This is not what you want. You want this variable to be, you want this no, the people that did not develop the people that did not die, maybe they dropped out or whichever one, but they did not develop the event. You want them to be 0, while you want this category to be 1. So you have to recode this new variable that you've encoded. You have to recode it by saying recode this, open a bracket. This category of persons, we say 1 is equal to 0. You okay, please, if you have any question, just call my attention. So you missed a step. Someone said you missed a step. Okay, where I use the encode command. Don't worry, please, you can watch. Okay, let me just do it. Let me just redo it. So I said the reason why you encode first is because the variable is naturally strings. And when your variables are full of strings, especially when you import from either a database or from Excel, you'll find out that you cannot do modeling with that variable because what we are doing is modeling. So you need to encode all of them. So that is what we are doing. Someone said, kindly use the drop down. The drop down will waste my time. I use commands more often. Is you know, we have limited time to this training. So let me just go ahead. So I said you recode these variables. You say recode that, open a bracket. these categories of people that are one, that's these people that did not develop the outcome, you call them zero. So you say one is equal to zero, and you say no, them this way. You open another bracket. This category of people that develop the outcome, you say 2 is equal to 1. And they are the people that actually died. So you say yes, whichever way you want to call it. And you generate a new variable. You can call it det2 or whatever you choose to call it. So this new variable now has, when you tabulate it, it has the labels of 0 and 1. You will see it now. It now has the level of 0 and 1. So this is one step. There is another step called, let me drop this. There is a shorter step. There is a shorter step whereby you just generate your new variable. You can call it generate depth. Is equal to 0, is equal to missing variable. Now, you want to generate a new column. This is how we generate new columns in Stata. So you generate the column and you call it nothing. That's full stop. Whenever you see full stop, it means, or dot, it means missing data. So generate this. So Stata generates this for you. And then you go ahead and someone is asking me a question. This was the problem. Okay, yes. You say, wait a minute. Okay. You say, replace, after you've generated, replace that, replace that if the variable called died is equal to yes. Replace that equal to 1. If the variable called died is equal to yes. So what you are saying is that for all the participants that these 31 participants, you want them to bear 1. So you want to replace them. So you do this and it has been replaced. And also say, and you say replace, you read the command and say replace equal to 0 if the participant that died is bearing no. So this 17 called them 0. So I had to do this because so many times your data may not be sent to you in Stata. It might be sent to you in Excel. It might be sent to you, oh, sorry. It might be sent to you in Excel. It might be sent to you in any format. So you have to work on it yourself to either recode or replace. So I have done this. Now you can, when you tabulate this variable called that, you can now see 0 and 1. So again, I want to record the drug and the sex. Just quickly, I'll say encode first, encode drug, comma, generate drug 2, and say drug, whatever it is I want to call it. Now I've encoded it. You can see the new variable here called drug. So then for the gender, you can say encode sex. encode sex, yeah, comma, generate sex 2. So for the analysis, we are going to be using this encoded variables here. And then this is our output. Okay. So we've done this. What's the next thing we are going to do? According to our slide, said, okay, open the data set if it's in stata form, import the data set if it's not in stata form. So when you import, you recode all your variables. We've done this, done this, done this, okay, done this. I've showed you how to import. We've done this. So what we'll now do is to create a do file and a log file. So why are you creating a do file? Of course, we have a do file already. You are creating a do file because you want to share the commands that you use for your analysis. That's why you are creating a do file. All right. You want to be able to show someone else the analysis you've done so that the person can reproduce it. So how do we create a do file? You come here and click on the do file. It pops up. So the do file was structured in such a way that you just run your command here. So you can see tabulate sex. You highlight it and click on execute. So it executes directly into your console, your results menu here. So, but already, so that we don't waste our time, I've already done the good job by bringing out all the commands that you need for your analysis from start to finish. So just open your do file. You don't need to do it again. So these are the commands we are now going to execute. And then I'm going to show you each line of code, what they mean. Now you see what we just did. You see what you just did. There are variables that we use for explanatory analysis. Something like describe, something like codebook, sum, list. Those variables are used for just to look at your data and see and have an overview of the type of data that you have. Now, instead of using encode command, you can use generate. You can use this to generate your so here I said to generate a variable called a gender. I said generate gender is equal to this, replace. So whenever you use generate, it goes with replace. So if you choose this as the one that is more convenient for you, no problem. But personally, I usually use encode and recode to do my analysis. It gives the same output, by the way. So all right. So once you've opened your do file, you can open a log file because you want to have an idea of your analysis at the end of the day. So when I open my log file, I usually would name it put a name, survival analysis analysis training analysis demonstration or training course. And I usually save it as log so that I can be able to open it with so many word editors. So I usually save my notepad, my log file with log. I will save it. So STATA will record the time that you open this log file. So whatever analysis, subsequent analysis that you are now doing, you'll be saving inside that log file. Yeah, someone is raising his hand. Please go ahead, Timothy, just quickly.
Okay, sir. Thank you so much. Please, I just want to add something on the log file that we are just doing.
Okay.
So usually, the reason why we are encouraged to add the .log extension is because if you use the .sml
Yes.
you will
SMCL.
certain that SMCL, thank you.
Yeah.
You can't share with anybody except the person has data. So that is
Exactly.
why it's so
Exactly.
important to
Yeah.
use the .log.
I've
Yeah, you could
noticed it.
always.
Yeah,
Yes,
true,
please.
true,
Thank you.
true. Thank you. Thank you.
Thank you,
Thank you
sir.
for, yeah. So when you use your log, you can always open it and share with someone, and the person can open it with even Notepad, even with MS. So it's easier to share. Okay, so we've opened our log file. So as we now analyze, our out, because data was not built in a way that it saves this and saves this and saves this all at the same time. No. So it's when you save now, it's only we can save the data for you in that DTA format. It cannot save your commands or save your output, unfortunately. So you have to use your log file to save those things. Now, what are the steps we are going to take now? Okay, we've done this. This is just a demonstration how you open and how you begin. I've created this. All right, so I told us that there are two windows. There are two windows instead of the edit window and the browse window, and they all are all used to visualize your data. But in edit window, you can't make any changes. In the browse, in the browse window, you can't make any changes. In the edit window, you can make a change as you want. So let's practice some of these commands to explore our data. So some of these things are not inside this. I'm not inside this file. So let me work with my command prompts proper. So let me do some little descriptive analysis. So for variables that are quantitative, you have age here, you have study time. These are quantitative variables. You use the command summarize, or you can say just sum like this. You say summarize age, and you see STATA will give you the mean, the standard deviation, the minimum and maximum. So it's as simple as that. If you also want to see more of the statistic descriptive analysis of age, you can say summarize age, comma D. So you are saying summarize age in details. So you would have this. Rest data will give you the median age, the 50th, that's the 50th percentile. It will give you the lower quartile age. It will give you the upper quartile age. It will give you the variance, your skewness, your kurtosis, your mean and median. Of course, you know that this variable is normally distributed because looking at it, I assume that it's normally distributed. The proximity between the median and the mean is quite close. So yes, someone is raising his hand. Is that an error?
Yes, I had this. I wanted to ask.
Yeah.
Because I think you are describing about some of the basic STATA skills,
Yeah.
of which I think a person who is coming to learn about survival analysis, we expect at least to have these basics. Because we have a lot of things in survival we don't understand. I think they should be given priority instead of insisting these basic STATA skills. Maybe you can have a parallel session for those who are beginners in STATA to do with that.
Thank you. Thank you. All right. I've noted that. So I will jump this beginning part. So let's go straight to our survival analysis. Now, the first thing you do, I mentioned it yesterday, is to declare your data as a survival data. If not, you cannot be able to do any analysis here, because STATA will keep seeing it as a normal variable if you don't do this declaration. So how do you do that? Look at the command. The command is stset. Please note, the command is stset, and this is your outcome variable. The study time here is your outcome variable. That is actually what you are modeling. So in basic STATA regression analysis, your outcome variable always comes first. You get. So you say comma, failure. So let's do this. Let's do this and let's see how it works. Let's do this. Wait. Okay. This failure not found.
I think we haven't declared the data to be survival data.
Yes.
Good.
Yes,
Yeah.
true. Okay. We should be able to work now. Or was it because
No, I think you're supposed to use depth instead of the failure. So you should set depth is equal to 1 for the failure.
True. Not because of the way this data was coded. Yeah, true.
Yeah.
True. So I'm going to adjust this.
No, not that one, the one in the bracket.
Sorry. I'm going to adjust this.
Okay. Yeah.
Let me tabulate this outcome first. Okay. This should give us what we are looking for, right? Okay.
I think it should be the depth. Can you browse the data again, please?
Yes, that's what I want to be sure. Okay,
yeah, browse it again.
Died, not that. I think I used died. D-I-E-D. D-I-E-D. So, okay. Oh. This, you know, this do file was written. This do file was written with the data I brought from.
To be very sure,
use the depth. D-E-A-T-H.
You can browse data to see the labeling in the data.
Yeah, good.
Oh, thank you. Yeah, thank you. Yeah, okay.
Yeah.
Yes, so we can now go ahead. True. Yeah. Okay, so in this scenario, our outcome variable or our event is death. So I think yeah, thank you for calling my attention to that. All right. So we've declared that our data is survival data. Anytime you do this, anytime you come to do your analysis, I usually prefer the data to be in data format instead of Excel, but it's fine. So the next thing to do is to compute your life table. Now, look at what the output that we have here. We have 48 total observations. Someone is asking, why do we declare data? I said the reason why we declare data is to declare the outcome, because ordinarily, when you do this, when you have this study time and you have died here, STATA will not be able to guess the one that is your outcome here, whether it is the people that have died or the people that did not. You know, outcomes can change. It mustn't be that. It can be any other thing. It can be remission. It can be recovery. So the reason why we declare data is to let it know the outcome variable specifically, and also to generate this for our outcome, that's the event. Sorry, to generate this for the event and to generate the t variable for the time. I hope I did justice to that question. Okay. So I was talking about someone is still asking. Okay, thanks, thank you. So you have 48 total observations here. You have 0 exclusion. We have a 31 failures. That's 31 people that died. Remember that the failure is your event. And you have 744 total analysis. And so this is our event has been declared successful. So the next thing is to compute what we call the STATA descriptive tables. the life tables that just show us the estimates and how just a minute, okay? That shows us the estimate of your survival. Now,
I think now we
will
need
keep
to
changing, yes.
Yeah, exactly.
This will keep
Exactly.
changing to deaths. Please take notes when you are using this to find, please, so that we don't run into some of these small errors. Thank you. Okay. This is what we call a life table. It gives us at different intervals. This is number of deaths. This is number of people that were lost. This is this is the survival rates. This is standard error, and this is your confidence interval. Many a times we don't report this life table this way. We use intervals to report it. Because imagine when you have thousands of data, or when you have a lot of data, if you report this table this way, it will be very large. So you can report it by an interval of 5, an interval of 10, an interval of 2, an interval of, depending on what you want to do. So that is why we add this command here, this extra command called interval. So change your variable here, and then you see the difference. You see what theta will do now. Now from 0 to 5, look at the number of deaths and look at the survival estimate, 0.87. It is highest in this particular interval. From 5 to 10, look at the number of deaths. Look at the survival estimate. From 10 to 15. So you can have this at an interval of 2. Let's see, at an interval of 2. It mustn't be, yeah, just someone is raising his hand, just a minute. It mustn't be 5. So you can have this way. Yes. So please go ahead.
Okay, I thank you. I think yesterday one asked that those interval, it was I think 0 to 5, and you said that's constant. So I think I need to understand about the interpretations of all these components here and what do really exactly mean, and how do I link with maybe if I have a certain study I'm evaluating. Yes.
Okay. Normally when we do this, well, it is not in all cases. Ordinarily, what I need to read, for example, if you are doing survival analysis and you are doing your work in a real life example, a scenario, sorry, all I need to see, if I'm the one that is reading your work or analyzing your data, what I will produce, I won't produce this table for you. What I'll produce for you is a survival plot. That's the Kaplan plot. I'll do a log rank test for you to see the difference, whether there is a significant difference between whatever groups you are comparing. And if you have a lot of covariates and other independent factors, I can go ahead and do a Cox regression analysis for you. So, but this table is I don't know how to bring it to, okay, let me relate it to this scenario. From the interval, now look at these data sets. Look at the study time. You know this time is in weeks. So we have 1 week here, at week 2, at week 3, at week 4, at week 5, like that. So we want to see at this interval, this time interval to this time interval, what is this? What is the survival coefficient, or what is the survival rate? At this time interval to this time interval, what is the survival? It's just a descriptive analysis. It's not comparing anything. So that's why we call it a survival table. Now, you can say, let me repeat for 5, let me put an interval of 5, that between 0 to 5 weeks, What is that is the time period that we recorded the highest of 87.5%. That is the time period that we recorded the highest survival rate. The time period that we recorded the lowest survival rate is 35 to 40 weeks. The actual this data was collected from of course from to 40 weeks. So 40 weeks is the maximum. So this is 19 points. Yes, you are still raising your hand. Go ahead. Go ahead. This is 19 points.
Yes. So in that we can say for this already computed data, like within that study time of between 0 and 5.
Yes.
About 6 deaths occurred.
Yes. Nobody was lost.
With the survival rate of 0.88 with that 95 confidence interval, right?
Exactly. Exactly. And then nobody was lost, nobody was censored within this time period. So if you want to see where was the censoring highest, you see it was highest between this time period, 15 to 20 weeks, because we have 4 here. And where did we have at what point did we have the highest number of deaths? See, it is between 5 to 10. So this is a descriptive rundown of someone is still raising his hand. Someone raised his hand. Moses, you raised your hand.
Yes, yes, thank you so much. I wanted to appreciate for the survival analysis we ran. Are there cases where you have the survival rate increasing as the follow-up? Compared to the number of as we follow up. For example, so for example, having the survival rate highest as you go down. Is this the trend? Should the trend always be from the highest to the lowest?
From the highest to low. Of course, you see,
it depends on the study.
you know, when we do the Kaplan-Meier plot, you understand this better. You will see how the probability of your survivor goes from 0 to 1. It doesn't move from 1 to 0. Yeah, so on the x-axis of the Kaplan-Meier plot, you will see is because we always say it's from 0 to 100%. That's from 0 to 1. So you will now see how the plot for each person that died, for each person that developed the outcome, you see a dip. For each person that developed the outcome, you see a dip. It keeps dropping at different time points. So this is just a brief description of what happens in that curve. So we are going to tally that curve with what you have in your life table. You will see that it is exactly the same thing. So your life table will help you to understand what is, because the curve can be very complicated. You may not see, especially if your data is large, you may not see what is really happening at every time point. But with your life table, someone is asking, I'll share the recording. Yeah, thank you. With your life table, you can track the Kaplan-Meier plot. So let's hold on till we get there. Okay, so I've shown you guys how to do the life table. Now you can also expand this by a categorical variable. You can expand it by sex. You can expand it by drug. You can expand it by, depending on how you want it. You want to see the distribution of these survival estimates by male and female. You can run this at an interval of 5. Still at an interval with an interval of 5, you can run this. You have your variable here. And then the only thing that changed is by sex. So we introduced it at this point. So you can have this and run it. So let's see what is happening in males and what is happening in females. You could see for 0 to 5 weeks, the survival estimate of males and females were basically okay, they were the same, nothing changed. But for 5 to 10 weeks, we had females surviving more than males. So this like this, like this, like this. Now let's also do the graph. Let us do the survival graph and see a summary, a holistic summary of all this. The survival graph is just the is a very simple command, the STS graph. Now, if you plot this, watch out. Watch out for this graph. If you look at this graph, you will see how the probability, this x-axis is the probability of survival, while this y-axis is your time. In our data, this time is, hello? Okay. In our data, this time is calibrated in weeks. So from 0 to 40 weeks, what happened? From a probability of 0 to 100, a probability of 0 to 1, what happened? So you see, at 10 weeks, if you trace this value here, if I had a ruler or at a pointer to trace this value here at 10 weeks, you can see that it fell between 0.6. Yes, at 10 weeks, I think it's at this point. If we trace it to the y-axis, it fell between 0.6 to 0.65. So you could say that there are 65% chances of people having the event, which is death, at 10 weeks. You see? Now, you see a steeper dip here. All these dips represent death, which is the outcome. And then for each, what is the probability that more people? So if I ask you where the probability was higher, you could trace it to this dip. This dip here is larger than this dip here. This dip here is a bit, I think, they're equal to. So if you trace the survival time here, you see that it's between 22. This should be around 22 weeks. So at 22 weeks, the chances of the event happening was getting smaller. At 38 weeks, this should be 28 weeks. If you trace it here, you see the chances were getting smaller. Here, the chances we are getting smaller. So that is why it arranges that table, that life table, from highest to lowest, because the graph plots this way. It does not plot this way. So when you run this graph by let's say drop, in this case now our drop is a small letter. When you run this graph by drop 2, this is the variable that we have. Drop 2, for example, you will see, yes, you will see how the people that are on placebo, which is drop 2, are here. They have lower survival estimates than the people that are on other type of medication. They had higher survival estimate. Yes, ask your questions. Paul, sorry.
Okay,
please,
thank you.
Yeah.
Yes, so the left side is the probability
x-axis. Yes, probability of survival.
Okay.
Yeah.
And y is
your time.
I mean the
time to
y
event.
is the probability, y the x is the time.
Sorry, this is your y. Sorry, I keep mixing it up. Yeah, this is your y. This is your y. Probability.
So yes. And so on the graph, how can you modify the time? Like maybe you are following cancer patients in maybe for 5 years or for 2 years, then you want to do 2 months in monthly basis, or if you want to account them in years, year basis, how will you make those how will you put your scale? How do you scale your data? It's within your data, your original data sets, or can you do like the previous tables that we had been discussing?
Okay, if I understand what you're saying, you collected the time when you were doing your study. How long did you follow these people up? Was it in weeks? Was it in months? Was it in years? Your time should be defined. Is it an outcome that will happen in weeks? Is it an outcome that will happen in months? Is it maybe long-term illness that will happen in years?
Okay, so my concern was from the previous data that you have run, of which you were able to set those intervals.
Okay. Okay.
So I was asking if those intervals applies in this graph.
Well, when I collected the data, I calibrated them in 1 unit. I can't have some in years. I have some in weeks. I have some in months. My time variable must be uniform across board. Do you get that? Your time variable should be uniform across board. If your outcome is happening in weeks, then all of them should be in weeks. If it's happening in months, all of them should be in months. If I really get what you're asking.
Okay, my concern was because we were asking at on the previous tables, and then you told us that we will understand well when you come to the graph. So I thought that there is a linkage between those tables and the graphs. That's why I asked on those categorization.
Yes, of course. Let me place the two side by side so that you understand the relationship between the two. Someone is Peter. Yes, go ahead. Someone is raising his hand.
Yes, good evening, Doc.
I think you can proceed to explain.
Okay. Yeah, go ahead.
Good evening. All right. Please, sorry, I don't know if this question has been asked. I just joined. Okay. But when I joined, I heard you say that one of the groups have is it a better survival time than the other? I don't know if that statement is correct. But how do I know that from this
lower survival
chart?
estimates, not necessarily time. What we are measuring here is the probability. That's the chances of survival. Probability is chance, likelihood of survival. So it sees I increase, it goes from 0 to 1. It moves from 0 to 100%. So this graph that is on top, this group of people that received other drugs that are not placebo, they are assumed to have higher survival rates, survival estimate than this group. Did you get, Peter?
Yes. Is it by drawing a line across to meet
now, for example,
both graphs?
No, there is no way these two graphs can meet. For example, if you look at the 20th week, week, if you see this person that took the placebo, look at their survival time. Look at their chances of survival. It's much lower. Trace that same people to it's much higher.
I get it now. I get it now. Thank you so much.
Yeah. Someone else is raising his hand. Yeah, Martins Martins, go ahead.
Thank you very much, Doctor. My question is about how do we integrate the hazard ratio in this Kaplan-Meier curve?
Okay. How do
we integrate the hazard ratio in this Kaplan-Meier curve? Yes.
Okay. The hazard ratio comes in at when you do your Cox proportional hazard regression. This Kaplan-Meier curve shows you the distribution of when you do your Cox proportional hazard, that is where it will give you the coefficient, and which is the exponent of the coefficient, the hazard ratio, which you interpret as the odds ratio. So you can't see it from this graph. You see it when you do your Cox proportional regression. We'll get there. When you have covariate, when you have other independent variables that you want to control for. Just like in logistic regression, when we have our outcome variable, we have other predictor variables that we want to use to control. Maybe those variables can be confounders. So that's something that we do here. Our outcome variable is our study time, which is our what we are predicting, the time to event data. And then every other thing that comes in will be covariates or independent variables. That's your predictors. So
all right,
we use Cox proportional hazard ratio to now tell you this is the ratio of the hazard over this. It would likely the hazard here would likely be more than the hazard in this group. So that's the last thing we are going to do.
Okay, thank you very much.
Okay, so someone said I should finish the presentation before answering questions. You know, this is a practical class, so I would like to be taking questions at each point so that people don't get disinterested. Yeah, Moses, you're raising your hand.
Yeah, I had the same suggestion, but
okay.
That you prefer it that way, then it's okay. Yeah.
All right, now let's go ahead. If this is your first time or you are not so familiar with this, this is just an introductory lecture. You can now, at the end of the session or at the end of the training, go ahead to personally on your own. You have all these materials, so you can study them and use them at your leisure time and no more. I wanted to keep it as introductory as possible because I see a lot of people when they have this kind of data set, you see someone that is doing a cohort study. The person will be using the wrong analysis. You'll be doing binomial logistic regression, doing other types of regression that doesn't account for time. So I thought it wise to put up this course and I just raise the awareness and have people have this so that you can now take it off from there. So personally, it's been quite a long time I did survival analysis like in my work because you know, longitudinal studies are not common. They are mostly funded and then it takes a whole lot of time. So this kind of analysis may not be it may not be the usual day-to-day analysis that you do in your work, except if you have a fully funded study where you are following people or what you are following people to develop is very short. Maybe pregnancy outcomes that you can just see in 9 months. So, but if you are following people to develop a disease or to die or to develop an event that is that will take time, I bet you that survival analysis will not be your day-to-day analysis that you do, but it's fine. Okay, so let me go back and tally the Kaplan-Meier plots that we just did with the live tables. Someone said it doesn't see how the two of them. Now look at this live table. As you see here, at the beginning of the study, the survivor was highest. As the time was reducing, of course, at 40 weeks, you can't expect the survivor to be. More people is expected to die because the event is death. So at 40 weeks, you can't expect the survivor to be this high. No. So the survival estimate is 19.8%. So if you place it side by side with this curve, let's do the curve again. Sorry. If you place it side by side with this curve, you will see that as the time was increasing, this is the time on the x-axis. As the time in weeks was increasing, and then the probability or the chances of survival was also increasing. Now, you will see that is a negative association. If this is a correlation graph, we will see any graph that comes like this means that as this one was increasing, this one was reducing. If it's a positive graph, you will see it going this way. So ordinarily, you should know that as time increases, survival decreases because these people will come to a point that they will either develop the outcome or they will pull out of the study. Now, look at this group, the placebo group. Look at how they fared. At 20 weeks, they had lower chances of survival. But when they started the study, they had higher chances of survival. When they entered the study at this point, everybody started at 0, because before you collect your survival time, you need to whether the person entered the study after 5 months, you need to there's a way we do it so that you can shift the time period that everybody will start at 0, because this curve will not accommodate people that entered later. No, everybody starts at this 0 point. So, but you can see that for this person that were on this drug, at the same 20 weeks, they survived, their probability or their likelihood of survival was higher than this group. So if you are making the postulate that people that are on placebo, let me say that your null hypothesis, or your hypothesis that people that are on this drug will survive more than people that are on this drug. Let me repeat it again. People that are on this drug, that are on placebo, whatever it is that you gave them as placebo, and people that are taking other drugs, and then you follow them up for a period of time, at the end of the day, who had more survival chances? Is it this group or this group? It's definitely this group. Look at their curve. Their curve was much more higher. So eventually everybody developed the outcome, but the question is, at the end of the day, when did this person develop the outcome? And then who survived better? Who had higher chances, higher probability of survival? That is what the Kaplan-Meier plot tells you. It doesn't give you hazard ratio. It doesn't give you whether the estimates were significantly different. No, it just gives you a descriptive rundown of what happens between the groups that you are trying to follow up. Now, if you want to see whether there is a significant difference in survival rates between this group and this group, you do a log rank test. That's the next thing you are going to do. The log rank test tells you whether there is a difference in survival rate or survival probability or not. But you can't see it from this point. Okay? So you can have as much group as you can. We can look at this, the survival rates in males versus females. Let me use sex 2. Remember, I've recorded my data here as sex 2. So let me use sex 2. Let me see in males and females who survive more. Look at males and look at females. Look at the estimates of the estimates are almost the same, but you see, the chances of survival in males was much higher. The chances of survival in females. Yeah, someone has a question. Tamani, just 30 seconds, please. Go ahead.
Oh, okay, thank you. Sorry to bring you back to the previous graph where you had the survival rates. Yeah, given the two different drugs that they took. So are you able to add another variable to that Kaplan-Meier graph to see how the reaction of the drug may be given their socioeconomic status?
Okay.
I don't know if I don't know if that's a good example, but yeah, something like that.
All right. So when you want to see both the drug and maybe male and female, you want to see by socioeconomic status, you want to see maybe by occupation, by another variable. You want to add a third variable, right? That's what you mean?
Yes, perfect.
Okay. I just hope that the curves will not the curve will not deceive you, because it will be difficult to trace. The estimates will be difficult to trace when you have something like 4 in 1. So it's better you have it this way. It's better you have it this way. If you want to add, let's see if I can add by sex. Can I add another variable here? I've not tried it before. And let me see sex identity. I don't think STATA can contain a new variable. I don't think so. Let me see. Let's see. Do I have another categorical variable here? Yeah, no. Do I have? This will not run. I'm not sure. This will not run. So, is either you look at each variable by variable, categorical variable by categorical variable individually, so that you can estimate your probability.
Hello, sir.
Yeah.
Please, what about when we add the if statement? I don't know.
The if statement. Okay, give me an example.
In case you want
example.
to.
If, yeah.
So, that is if you want to do it by the drag.
Yeah.
Then you check the code for the if drag. I don't know if it will work.
Yeah.
Let's try it and see.
It's equal to placebo, right? Something like this.
Yes, please.
Okay. Unfortunately, he gave us.
Okay, let's bring the if after the graph. Let's see.
Someone says by drug 6.
Okay.
By drug 6 like this. Let's try. Still didn't work.
I think you have three. You have three. Yes, you have 2 6. I don't know if it sounds okay, but yeah.
Sorry.
And then a space between drag and 6. Yeah. Oh.
Yeah.
Can I have a space between drag 2 and 6 too?
All right. Interesting. Thank you.
This is nice.
This is nice, but it's confusing, is it not? How do you read this now? That's the issue. No. Reading this will be difficult. Okay, it's nice. It's nice. If you don't have, maybe in your paper you don't have enough space to. Yeah, it's fine. It's nice. It's nice. Okay. So we have females that took other drugs. We have females that took placebo. We have males that took other drugs. And we have males that took placebo. Okay. So the group that had the better or the best survival estimates were females that took other drugs. Interesting. Followed by this group, males that took other drugs. Okay. Generally, people that took other drugs, they did better than they survived more. Their chances of survival was higher than this group. Okay. The placebo group. Oh, interesting. Thank you for that. Thank you.
You're welcome.
Yeah, thank you, sir. All right. So let's see if there is a significant difference in survival estimates between the people that took the drug and the people that took the placebo, the two groups that we've been studying. That is where you do your log rank test. So your log rank test is likened to the t-test or the independent sample t-test that you do to see whether there is a mean difference between this group and this group. Okay, so this is the command STS test. You put your drug or your variable, that's your independent variable, and then you say comma log rank. So let's see what do we interpret by this. Oh, variable drug not found. Yeah, I remember that we have changed the name to not drug now. We've changed it to drug 2. Yeah, drug 2. Yep. So you could see that the survival estimates in this group versus this group. So if you have a hypothesis that is stating that instead of looking at this participants one after the other and looking at their time, you just want to see Or maybe one of your objectives of your study is to say that the survival estimate in this group of patients that took this drug versus the other group, even though that one was higher than the other, there was a statistically significant difference. You know that generally in statistics, if something is not does not show statistical significance, it merely could have just occurred by chance. So that this group had a higher survival rate than the other group may have just occurred by chance. So, but you want to know, is it the difference that you saw in the estimate, was it statistically significant? That is where you introduce this test that we just did. So look at the p-value here. Of course, your two-sided p-value. Thank you. Thank you for the comment. Okay, so look at your two-sided p-value. It is highly significant. So you could say, you could adopt your alternate hypothesis. Because the alternate hypothesis, you always say yes, that there is a significant difference in survival estimates of people that had other drugs versus people that were on placebo, that were placed on placebo. Your null hypothesis will say there is no statistically significant difference. So you could, at this point, the hypothesis to accept, of course, you know that it will be your alternate hypothesis and you reject your null hypothesis. So this is what the log rank test does for you. Now, unfortunately, the log rank test does not have the ability to contain other models. You know that apart from saying that the participants that were on placebo performed better, and the survival estimate in the placebo group was higher than the survival estimate in the other group, there might be some other confounders. There might be some other things like age. There might be some other things like gender. There might be some other variables that you can bring into this model to look at, to have a holistic view of what is really, really happening in your survival time. So unfortunately, the log rank test does not have that ability to contain other covariates. That is where the Cox proportional regression now comes in. So the Cox proportional regression will give you the hazard ratio. It will give you the coefficient. It will tell you this group versus this group. How is their survival? So just like when you do a logistic regression and you want to look at what is the probability or what is the odds that this group will do better than the other group, when after accounting for possible confounding variables. So you know that sex can be a confounder, age can be a confounder, especially in case control studies. Age and sex naturally are major confounders in case control studies because of the nature of human beings. So these other things can be brought in at this point. So that will introduce us to the Cox regression analysis, where you are allowed, someone is asking a question, what if the observed event is less than 5? That does not apply here. The Fisher's exact test is the variance of chi-square that we always report when we have expected frequencies, 25% or 20% of expected frequency less than 5. I don't know whether it doesn't relate to what we are doing. Please, thank you. You learned that one in the normal STATA class. Okay. I believe I've covered some of the things that are here in the course of this. So at your leisure time or at your separate time, you can now learn how to use the drop-down menu to run some of these tests. Look at how you can run it. I think declare your data. How do you declare your data to the survivor? If you forget the command, you can simply use your graphical interface and do that. Okay. We have done this. Scripting here. How do you get your life table? We've done this. We've done this. Okay. It is at an interval of 5. Your life tables. Okay. We've done this. Looking at the Kaplan Meier plots, what does it tell you? Which group has higher chances of survival or higher probability of survival than the other group. Okay. Now we've done the log rank test that tells you that there is a significant difference between this group versus this group. You can also do female versus male, depending on your categorical outcome. Your categorical independent variable. Okay, so let's look at Cox regression analysis. We also call it proportional hazard model. It is used to test for difference between survival time in a group of patients. It is more accommodating than the log rank test. The log rank test will only tell you, yes, there is a difference between this group and this group, but it does not accommodate confounders. It does not accommodate other variables that may play in between your outcome and your predictors. So the log rank test only gives you the difference in survival times of different groups. Let's look at how do you do Cox regression. First of all, before you do Cox regression, what do we define as hazard? Remember that yesterday I said that you need to define hazard in line with this data. So in this case, our hazard is our probability of death or the risk of death. So we want to see what is the hazard ratio? What is the probability of the risk of death in this group versus this group? So your Cox regression will be able to give you your hazard ratio, which you can now go home with and say this group has the probability of the risk of death, or the probability of death in this group is lesser, or it's more likely to happen. It's less likely to happen. It is greater than the other group, having accounted for this, this, and this. Okay. So if you want to do the okay, so of course you should know the covariates you want to include in your model. Let me go back to the data that we have. If you look at the data that we have study time. This is our outcome variable. Yeah, the variable we are modeling. We have drug. We have gender, that's sex, and we have age. So we want to bring in this age now to factor it into our model and see our hazard ratio, our risk of death. All right. So this is the way we write the Cox proportional hazard ratio command. We say ST Cox. If you observe, you see that survival time, all your commands in survival analysis starts with ST. This ST that, so this is ST Cox, sorry. Your age variable, your gender variable, your drug variable. Remember that age is a quantitative variable, so it doesn't need to carry IB. Gender is a categorical variable, so you need to itemize it. If it's in logistic regression, when I do my modeling, I usually say I dot gender, I dot drug, I dot every variable that is a categorical predictor is important to include this in the command before that variable. We include this in the command before that variable. Now, what we have here now is instead of gender, we have sex2. I think that's what we have. According to the data that we have here, we have sex2 here. Please, just a minute. Let me attend to something. Okay, sorry, I'm back. So what we have here is sex2. And then for the drug, what we have here is drug 2. Yeah. Remember that this is our encoded variables, not this. Okay. So let's see. We've run our Cox regression modeling. We've run our Cox regression. Just like if you are familiar with logistic regression, it will be easy for you to explain. Just like the same way we explain odds ratio, the same way we explain risk ratio for case control studies, for cohort studies, odds ratio for case control studies. That is the same way we explain hazard ratio for clinical trials or follow-up or prospective cohort studies. Now, what does this mean? This is a hazard ratio of 1.11. Now, sometimes you will have coefficients here depending on the software that you use. If you are using maybe Arrow or you are using an online statistic calculator, sometimes it will not give you this hazard ratio here. It will give you just coefficients and it will keep the hazard ratio somewhere here. It doesn't matter. How you can get your coefficients, your hazard ratio from your coefficient is to exponent it. You'll see your hazard ratio. The coefficient is not a better way of interpreting. The hazard ratio is more just like the odds ratio and coefficient. So the odds ratio will give you in this group versus the other group what is happening. So let's interpret this. If you have a hazard ratio that is greater than 1, you say there is an increased hazard. If you have a hazard ratio, that is greater than 1, you say there is an increased hazard. If you have a hazard ratio that is less than 1, you say that there is a decreased hazard. If you have, now, when it is less than 1, you minus it from, if you have something like 0.6, let's take, for example, for each 1 year increase in age, and the hazard ratio here is 0.6. What it means that the participants have 40% lower hazard ratio. The participants have 40% lower hazard of death. So what is their chances of death? The hazard is reduced by 40%. When you have ratios that are less than 1, you minus it from 1. Now look at this age. Age is significantly associated with length of survival because look at the p-value here. It's a statistically significant. So you can say that age is significantly associated with length of survival. Now, when you have this, you can now describe the hazard ratio here. But look at the male gender. The male gender did not have any association with the length of survival. Look at the participants that are on placebo. Remember that every time you have a categorical predictor, automatically, the one that is alphabetically more arranged becomes the reference. I don't know whether we know about that. The one that is alphabetically, now, when you have sex, for example, if you tabulate sex here, you have females coming first before males. So whenever you do a logistic regression or you do a Cox, just as we've done, proportional hazard regression, this category here, that is the number 1 category, we go in as a reference category so that you can see the hazards of males, or hazard ratios of males over or when compared to females. So that is the way we interpret it. That males, someone is asking. Okay, someone said, can we say that being a male is associated with 20% higher hazard compared to female? Unfortunately, we can say that, but there is no association. You see, there is no association between the length of survival and being a male. So you will confidently beat your chest and say that when there is a significant association, first of all, here, people that are in the placebo group. Yeah. Do you understand now, Moses? People that are in the placebo group are 9.3, if it's an odds ratio, we say more likely to, the odds are more likely to happen. The odds ratio or the odds of the event happening is 9.3 times higher, or 9.3 times more likely to happen, because it is greater than 1. That is the same interpretation that the hazard of the placebo group is more likely than when compared to the persons that are in the other drug group. So this is 20%. This is 36.9% if you want to explain it by percentage. Or you can say 9.34 times increased hazard than the other group. Here you can say 1.20 times more hazard than the other group. Here you can say 1.11 or 1.1 times more hazardous than the other group. Unfortunately, I don't have a hazard ratio that is less than 1. So if it is less than 1, where we have maybe 0.6 or 0.5 or 0.3, anything that is less than 1, you interpret it in a way that you minus 1 from it. If it is 0.6 that is here, for example, maybe you have 0.614 or we have 0.64. What we will say is that a 1 year increase in age brings about a 40% lower hazard, or the hazard was reduced by 40% because it is less than 1. So that is how we interpret it. If you are conversant with the interpretation of odds ratio.
Is this 40% or 11?
He said this is 11%, not 40.
It's not 40%.
No, it's
yes,
not.
Thank you. Okay, thank you.
Either you say 1.1 times more hazardous, or you say 11.4%. Depend if you want to interpret by percentage. So many times I find it more comfortable just saying this is 1.11 times more hazardous for a 1 year increase in age. For males, this is 1.2. So, but if you are comfortable with percentage, no problem. So what I'm just saying that if you are using percentage for for a hazard ratio that is less than 1, you minus 1 from it. Now let's look at this p-value. Let's look at this p-value. Look at the p-value here. This is not significant. Look at the p-value here. This is not significant. If you observe, you see that 1 is not contained in this p-value. Sorry. If you look at the confidence interval here, this is 0.56 to 2.55. If you look at the confidence interval here, this is 3.83 to 22.89. The confidence interval here is 1.03 to 1.0. Now, who can tell me the relationship between p-values and confidence intervals? Is there a way one can actually know whether this p-value was significant without just by looking at the confidence interval? Because sometimes when we do, sometimes when we do regression or when we do logistic regression, we may not put this p-value, we just put the confidence interval. And then once I look at the confidence interval, I can know whether there is a significance or not. Oh, some people are raising hands already. Yeah, Moses. Do you have any idea?
Yes, thank you so much. So
thank you.
We consider, so if when we look at the confidence interval,
okay,
we always need to look for whether the confidence interval contains the null value or the value of no effect. So in a ratio, the value of no effect is a 1, where the hazards of exposure and non-exposure are equal. So in this case, for males, 0.5 and 2.5, there is a 1 before we go to 2.5. So that means that within this confidence interval, there is a 1, which is a value of no effect, meaning that the observed estimate is not actually significant statistically. And for the others, the first one for age and for the placebo, they are all above 1. So they are significant.
Very
good.
I
understand it.
Very good. So interpret this again. Sorry, interpret this first one again. So that
for the first one, the first one is so it's it's 1.03 and
Yeah.
1.2. So what I see here is that the confidence interval has is very narrow, or it's a more precise estimate compared to the one of placebo, which is a bit wide.
Okay.
But still, the confidence interval, the lower confidence interval is still above 1. So I would think that the observed estimate may be significant. It is significant statistically.
Okay.
That's how I understand it.
Thank you for that. Someone else is raising hand. Yeah, so yeah.
Okay, I just wanted to second what my brother has previously said.
Yeah.
But of course, by looking on the confidence interval, with the outcome, if it's a ratio, risk ratio, rate ratio, odds ratio we get, without even p-value, you can still decide and say like this is significant or not significant.
Exactly.
And the fact is the one which has been said that if it doesn't cross the null value, it doesn't include the null value, then that is statistical significance. One thing that I think I need to be updated is that if the difference or the interval is narrow, then that means it's more significant. I'm not sure with that, because if we can see even this group of placebo, it's ranging from 3.8 to 22 to yes, to 0.9, but it's very, very less than 0.001, less than 0.001 is compared to this age state, which is less than 0.005. So I don't think if the narrowness of the confidence intervals means that it's more precise as compared to those with the wide range confidence interval. But which makes something to be significant is that it doesn't include the null value, which is that there is no difference among the two groups. Yes.
Okay. Thank you for that. All right. Anybody else still raising hand? Okay. Okay. Thank you for your contributions. If we had more time, we would have talked about so many other things too. But it's fine. Okay, so the last other commands, let's also look at this let's look at this, what we just did. Let's look at it by gender, okay? Here we had, okay, I think this command was run 2 times. Here we have sex too, yeah? And job. Still the same analysis and the same result. I hope, okay, still the same thing. Okay, fine. Then finally, you see why how we went from the life table to the Kaplan-Meier plot, the log rank test, and now we are in proportional hazard ratio regression. It all depends on what you want to do, and it all depends on the analysis you want to carry out, and it all depends on your objective. Some people can just have descriptive objectives. So you see the table that we just interpreted. This is our age variable, 1.11. So we say for a unit increase in age of the participant, death increases by approximately 12%. So if you are using the percentage, you need to interpret it this way. This is 11.4, so we can say 12%. Yeah, it's fine. If you round it up to the nearest percentage. So because age increases in if this age increases in years, I usually say for a 1 year increase, because the unit of age is years, increase in age, the participant death, or death is our outcome, increases by approximately. So it means that as you are aging, your chances of death for this study, people that they collected this data for, increases by 12%. That is understandable in the real life. Then look at this drug. Look at this drug category. Remember, this drug is a categorical variable. So we may not be able to see the one that is the reference category here and the one that is not, because of the command that was used. You see, IB was just added. So, but in the do file I gave you, this command, I expanded it so that you can, okay, so that you can be able to see the group that is the reference category. Now look at this hazard ratio, 0.106. It is less than 1. We say that the risk of death is approximately 90% because this is 1 minus 0.10. Lower. It is lower because it is less than 1 among those who took the drug compared to those who took the placebo. So those who took the drug are the category that we are modeling, while those who took the placebo are our reference category. So that is how we interpret it. The risk of death, because this is hazard ratio. Remember, I said that the hazard here is the probability of death. That's the risk of death. So what is the risk that someone will develop the outcome, which is death? You see that it is lower among those who took the drug compared to those who took the placebo. So you can see that you can now make your deductions that the drug reduces the amount of time that these people die by 90%. Look at gender. This is 1.197. You see there is no significant difference across gender because the p-value is not significant. So whatever interpretations you are making from this ratio or from this estimator here will not be so important, because there is no association to start with between length of survival and gender and the male gender. So you could also make the female gender the reference category and see if there will be an association. So that is the way we interpret and we do our COPS regression model. So you can include as many confounding variables as you like in this model, bearing in mind that our outcome variable is the time to event. Time to event, okay? Then lastly, there is this very important assumption that we always do. We call it the global test. We always do before we do a Cox regression model. Of course, you know that every statistical test has the assumptions and some of the diagnostic analysis that you do. If you want to do a linear regression, you'll be told that the outcome variable and the predictor variable, the predictor variable and the independent variable must have a relationship. It must not have a collinearity. It must not, a lot of things. So many times, the real life data set may not meet all those assumptions. But you need to check them and be sure. So the global test is one of them. I just added a slide on this so that you can know how we do it and how we interpret it. In case you do your Cox proportion and someone asks you, how did you check for the assumption of, how did you check for the global test assumption? This is the command. We call it the test of proportional hazard assumption. Once you look at the p-value, now since the p-value of the global test is greater than the cutoff value, that's 0.1, and the p-value is 0.496, then the assumptions for the proportional hazard models are fulfilled. This is the way we interpret it. The long and short of. Someone is using his hand, okay? This is the way, I'm coming, Timothy. This is the way we interpret this, that the p-value of the global test is greater than the cutoff value of 0.1. So the cutoff value is 0.1. Once you run your test and you see that it is greater than that, you assume that your models, whatever assumption or whatever postulation you're making from your models is okay. Yeah, Timothy, please.
Okay, sir. Thank you. Please,
the cutoff of 0.1 is, I think, is a reference, is a standard. Just like when we do, sorry, Timothy, when we do the Shapiro-Wilk and the, what are those tests for normal distribution? Shapiro-Wilk, Krugman-Smirnov, Skinner-Skitosis test. You will always be told that once your p-value is greater than 0.05, you should assume normality. So it's, yeah, thank you. Yeah, Timothy, go ahead.
Okay, thank you, sir. Please, it looks like this is a post-estimation test, right? You have to perform the Cox before you do this.
No.
You
This
do this
should come first. This should come first.
Okay.
Yeah.
Okay.
Yeah, it's one of the most important
sir.
tests that you estimate first, and be sure that the assumptions for the model you want to run are fulfilled. You know, specific models have their specific tests that you do before, so that you don't run into making assumptions that are not that you cannot generalize to real life. Okay, and then yeah.
So what happens if the assumptions have not been fulfilled? For example, if you get a value of less than
0.1, right?
Yeah.
Of course, you will go for another type of regression. You know, this Cox proportional model. We have the parametric. Who is that? Okay. We have the parametric model. We have the semi-parametric and the non-parametric model. So you will need to go for another model if, just like in t-test, where we have t-test, and the other one we call Mann-Whitney, where we have Hanover and Kruskal-Wallis, dependent sample t-test, and Wilcoxon sign rank, Pearson correlation, Spearman's rank. So of course you have a model for when these assumptions are not met. But what I can categorically tell you, let me not make mistakes, is because this is not an analysis I do day to day. It's been very, very a long time I did this. So I wouldn't, in a case where you have your data not meeting the assumption of this test, I know that there are possibilities that you can transform your variable. There is provision for log transformation of variables that are not normally distributed, or you can go for another type of you can go for another type of hazard modeling technique that is not Cox. So you can check it out. You can check it out to be sure. Let me not say what I'm not so sure of. Yeah, thank you. Okay. Now and then finally, there is a graphical method too of checking, of assessing the proportional hazard assumption. So you can try that out. I think my slide stopped at that point. But I didn't hope to exceed here, because most of the, if you look through the articles that have been published on clinical trials, longitudinal studies, most of them will either do Kaplan-Meier plots or they will do Cox regression. It's difficult to see some of these other, like so many of them. I listed them out in some slides up there. It's difficult to see a scenario where, once you've collected your data properly, the survival time is known, your event is defined, you know who is censor and who you did not censor. Just go ahead and do your analysis. Most of the times, more often than not, it will meet some of these assumptions. Okay, so you have this slide everything about introductory level to survival analysis is here. You can always use it to do your own personal analysis at any time, any day. Also, you have the do file, so you can modify your variable there and run your analysis. And then with what we've gotten from this training, you can at least attempt to interpret. If you are confused on the interpretation, you can always go online or come to this slide. I think I added some interpretations too. It will always guide you. Okay. So thank you, everyone. Thank you for joining. And I don't know. Do you have any questions? Do you have any concerns?
Sorry, what is the procedure now for the certificate? Do we just send you an email and then we take it from there?
Okay, yes. For your certificates, honestly, I didn't intend to, I intended to make this completely free so that people can just learn. You know, in Africa here, we are limited by funds a lot. So there are a lot of these trainings that you want to attend, you have to pay and pay and pay. So, but when by the time I spent a lot of money in doing the network and the whole slide, and I just said, okay, anybody that wants to be certified can just pay a token. So I'm going to send you a link. The recording of this class will be sent to your email with a link that you can put in your full name, and then there will be an account that will be there. You can upload your proof of payment, and by next week, Tuesday or Wednesday, we'll start working on the certificate so that you can get it latest on your email on Thursday. So that link will carry your email so that everybody that's registered and paid will have their certificate. It's just a way of support. It's not mandatory. Just if you feel like doing it, it's okay. Like supporting, no problem.
Thank you so much. You've been so kind, and thank you for the wonderful class.
Thank you.
Thank you. Thank you. I have a question.
Yes.
About the test for the normality with the other tests. Those assumptions, in case you do, and then maybe one or two do not meet the test, the assumptions, what do we do?
If in a normal setting where you want to analyze data, right? It doesn't meet the assumption of normality. Is it assumption of normality? Okay. There are two things
maybe,
you do.
Maybe it meets assumption of normality and doesn't meet the assumption of homoscedasticity, or either of them, or both.
It's a tricky place to be, honestly. You won't throw away your data. You will look for another. I think there are other types of regression too that you can do in such a scenario. There is the unpopular. There are so many regressions that are unpopular. There are. I'm not a statistician by training, so I will not say much. But I know that real life data sets many times may not be able to meet all those assumptions perfectly. It may not. It may not. But if it meets 4 out of 6, you are good to go. Or you go non-parametric. Yes, there are non-parametric tests available.
Okay.
Yes, please. If you are joining outside of Nigeria, I don't know. There is no other way of paying than to pay in dollars. I don't know. Is there a way of paying in Naira here? I don't know. Okay. So I think just $5. Yeah, just $5. You can convert your currency to dollars and pay. If you can pay in Naira, no problem, you can. Yeah, the training for the STATA comprehensive course will start on the 10th of August. So I will also send a general email to everybody with the flyer. If you're interested to join, if you want to build your skill more, you can join that class. It will be a 8 to 10 days class of comprehensive step-by-step STATA training. Yeah, thank you, everybody. Yeah. Do you have a question? Amanda, someone is asking, can one do surveillance analysis on secondary data. What do you mean by surveillance analysis?
Hello?
Yes, go ahead.
So my question is, if somebody have a secondary data, let's say like surveillance data on measles or something, yes. Can you do survival analysis on that data? With that
data for you to do survival analysis on data, the data must meet a criteria. Are you following people up? You don't just do a survival analysis on any data. Have you concluded the follow-up? Did you define the time at the point you started following them up? That's one. Did you define your events? Has all of them, has the time for the study elapsed? These are the questions you need to ask. So if yes, then you can do survival analysis.
So why I ask is because
go ahead.
Yes, because